let's learn about how we can calculate volumes using the disk method. Now we're going to let f of x be a continuous and non-negative function. And we're going to define R to be the region bounded above by the graph of f of x and below by the x-axis, on the left by some line x equal to a, and on the right by some line x equal to b. So let's draw a picture to try to capture this scenario. So we're going to draw a set of axes over here. There's a y-axis. Here's an x-axis. We got x equal to a. We got x equal to b over here like this. We've got some function f of x like this. This is y is equal to f of x. We are going to have our left boundary be this line, x equal to a, and the right boundary be this other vertical line. This is x equal to b. This one was x equal to a. And the region R that we're working with is the region bounded by all four of those lines, the f of x, the x equal to a, x equal to b, and the x-axis. So maybe I'll even shade this over here like this. So this is the region R that we are rotating, okay? And we're rotating around the x-axis. So I always like to put a little loop here to indicate they're rotating about the x-axis. So if we have this type of situation, then the volume of the solid of revolution formed by rotating this region R around the x-axis is given by the following formula. It's going to be the volume is going to be equal to the integral as x goes from a to b. We're going to have pi times f of x squared dx. So this is our volumes by slicing formula using the disk method. Okay, so let us look at an example together. In example 3, it says, use the disk method to find the volume of the solid of revolution generated by rotating the region between the graphs f of x equal to the square root of x and over the interval from 1 to 4 around the x-axis. So I think the first step we should do is we should, graph the region. Okay, so let me draw an x-axis, a y-axis here like this, an x-axis here like this. Here's x, here's y. We're going to have a 0, a 1, a 2, a 3, and a 4 like that. We're going to have a 1, 2 like this. I'm going to draw my graph in blue. So we know the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2. So my graph is going to look like this. Like this. This is y is equal to the square root of x. Okay. We also have this interval from 1 to 4. So let me draw a vertical line here. Here that's x equal to 1. And then another vertical line here, that's x is equal to 4. And I'm rotating about the x-axis. So I'm going to put a little loop there like that. And, I'll just shade this region because I can. So this shaded region is the region R that we're rotating about the x-axis over here. The second thing I want to do is I want to set up my integral. So how do I set up the integral? Well, I definitely need to first figure out the region of integration is going to be and what the variable of integration is going to be. So one of the keys for the disk method is that we always chop up perpendicular to the axis of rotation. Perpendicular to the axis of rotation. Okay, so what I'm going to do here is because the x-axis is the axis of rotation, I'm going to chop up perpendicular to that. That means I'm going to chop up this way, like this. So I'm going to take my green marker and just chop it up like this. These are going to be the slices that I have. Okay. So what I need you to notice is that when I have this slice like this, and I rotate this around, I'm going to get a disc. So I'm going to get a disc that maybe that looks something like this. If I were to work with this piece right here, then you can imagine that that disc down here looks something like this. Where the x-axis is kind of going right through the middle of it. So this is the x-axis right here. Okay. And what I need you to see here is I need you to see that we have a little bit of thickness. This little bit of thickness, the thickness of the coin, that's playing the role of dx. So I know I'm going to put a dx at the end over here because that little bit of thickness lies on the x-axis. Okay. Once I've identified what that variable of integration is, then I want to look at my picture and I want to see what's the smallest my x value could be, and what's the biggest my x value could be. And when you look at the shaded region, the smallest x can be is 1, and the biggest x can be is 4. So this is going to go from 1 to 4. And then the last part is I just have pi times my function f of x quantity squared. So you should recognize this. This is just the area of a circle. And the radius r is equal to f of x. Okay, so now I'm going to substitute. So I'm going to get my integral is going to be from 1 to 4 pi times the square root of x quantity squared dx, like this. And I guess step 3 is going to be integrate. So actually we could simplify this first. So let's simplify this. This can be the integral from 1 to 4 pi. The square root of x squared is just x dx, like that. Okay. So I guess the third step would be you got to integrate. So my integral is going to become my integral is going to go from 1 to 4. I can factor that pi constant out. I'm going to have an x dx like this. Now I got to calculate the antiderivative. That's going to give me pi. The antiderivative of x is x squared over 2. I'm going to evaluate that as we go from 1 to 4. This is going to give me pi times 16 over 2 minus 1/2. That's going to give me 15 pi over 2 units squared. And let me highlight that answer. That is our final answer here. All right. So just as a quick recap, first thing we're going to do is we're going to graph our region, try to draw a pretty accurate graph. The second thing we got to do is you got to set up our integral. To set up our integral, first you chop up perpendicular to the axis of rotation. Look to see where that little bit of thickness lies. That little bit of thickness lies on the x-axis. That's why we have a dx integral. Look at the smallest and largest values of x that you have in that region. It's going to be from 1 to 4. And then just substituting the f of x into your formula for a circle because the cross-sectional area is a circle. After you've got it all set up, the last part is just to integrate it. All right, everyone. We'll look at more examples together in class. Take care.